Hello, this is Jack Jackson. In our last video, we introduced the idea of distributions of proportions based on either a hypergeometric or binomial distribution. And at the end of that, we worked an example of each, one based on a hypergeometric and one based on a binomial. We're going to look at a couple more examples this time. And this time, by now, hopefully if you've seen that last video, you can work through these on your own. So I'm going to be presenting a problem, asking you to pause and work it yourself, and come back and check your work. Okay, so let's take a look at our first example. There are 80 faculty members at a college. 60% of them hold a doctorate. A random sample of 18 faculty members are chosen from this organization for an advisory committee. What is the probability that there will be more than 70% of the committee who hold doctorates? Okay, press pause and work this out now. Well, notice that there are capital N equal 80 faculty members in a population, and M equals 0.6 times 80 equals 48 of them hold doctorates. We're sampling a group of N equals 18 of them without replacement. If X is the number of faculty members on the committee who hold doctorates, then X is a hypergeometric random variable. So we can use our HGO-CDF program of the TI-84 or the HGO-CDF function on the TI-Nspire to answer this question. The probability that there would be more than 80% of the sample who hold doctorates is the probability that the p hat is greater than 70, that should say. So this turns out to be, let's see, the probability that p hat is greater than 0.7. So the corresponding p hat is x divided by n. So multiply n times both sides here. And we get x is greater than or equal to 0.7 times 18. 0.7 times 18 is 12.6. So we need the probability that x is greater than 12.6. Well, that turns out to be the HGO-CDF of 80 for this population size, 48 for the number of successes in the population. 18 is the sample size, and then the number of successes in the sample has to be greater than 12.6, so that will be from 13 up to 18. All of these numbers input have to be whole numbers. So we start, no, we don't put in 12.6 or 12.7. We go up to the next one that can actually happen that's actually greater, the smallest one that's actually greater than 12.6, which is 13, and go up to the highest one which could happen, which is 18. So either here it is on the screen of the way it looks on the TI-Nspire, or if we did this on the calculator, we'd be putting in these values in this order: population size 80, successes in the population 48, sample size 18, lower bound on the x's 13, and upper bound 18. And either way, we're going to get about 17.7%. All right, here's another one for you to do. There are 120 people in a student population. 45% of them actually support Sarah Jones for student body president. A random sample of 15 students are asked who they support. What is the probability that the survey will report somewhere between 40 and 55% inclusive in favor of Sarah Jones? Press pause and work this out yourself now. Okay, well, if you're back here, let's take a look at what we got. Notice there is a finite number, 120, of students in the population, capital N, and it is known. Capital M is 45% of that, 120, so that's 0.45 times 120 is 54 of them support Sarah Jones. And of course, this would always have to be rounded off to a whole number, which it worked out to be a whole number this time. We're sampling N equals 15 of them. Little n is 15. And we let X be the number of Jones supporters in the sample, then X has a hypergeometric distribution. So the probability that the sample will have between 40% and 55% inclusive in favor of Sarah Jones is the probability that p hat is between 0.4 and 0.55. In other words, 0.40 is less than or equal to p hat, which is in turn less than or equal to 0.55. Multiply everything by the sample size of 15. 15 times p hat is x, and 40 times 0.4 times 15 is 6, and 0.55 times 15 is 8.25. So we need x's between 6 and 8.25. Well, there's nothing, the probability between 8 and 8.25 is there's nothing there except at 8 itself. So we're going to, this is the same as the probability that x is between 6 and 8 inclusive. So on the Inspire, you can see the picture here. It's HGOCDF of 120, 54, 15, 6, 8, or run your HGOCDF program on a TI-84. Basically enter the same numbers in the same order. Population size 120, number of successes in the population 54, sample size 15, lower bound on x is 6, upper bound on x is 8. X is the number of successes in the sample. And you work out that probability. So the probability that x is between 6 and 8 is 58.4%. That's exactly the same probability as the probability that p hat is between 40% and 55%. Okay, another application. 45% of likely voters support the Democratic candidate for president. What's the probability that a survey of 100 likely voters will report 50% or more supporting this candidate? Work this out on your own. Come back when you're ready. Press pause now. Well, notice even though the actual number of voters out there for president, capital P, so maybe this is president of the United States, that's huge, huge number, millions of people. We don't know how many it is exactly. So the fact that we don't know it means we can't use a hypergeometric distribution, even though it probably technically is a hypergeometric distribution. We're going to assume the probability of successfully selecting a Democratic supporter for the Democratic candidate for president is 45% for every voter we select. Even though we're doing this without replacing them, we're going to consider this a binomial distribution for x being the number of Democratic supporters. We know the survey is little n is 100 is the sample size for the survey, and how many of those will report 50% or more of the survey? What's the probability the survey will have 50% or more supporting the candidate? Well, okay, so let's see. This turns out to be the probability that p hat is greater than or equal to 0.5, which means the corresponding x is greater than or equal to 0.5 times 100, or 50 in other words. So if x is greater than or equal to 50, the proportion of successes in the sample is more than 50%. So now this is a probability to the right for a binomial. If you have a TI-84, the way you're going to run this is you're going to get 1 minus the probability that x is less than or equal to 49. So here I'll actually show this typing in. Now remember, the binomial CDF on the TI-84 only goes from 0 up to the x value. Well, we want the probability from 50 on up higher. So what we want to do is we want to subtract from 1 the probability from 0 up to 49. Okay, and that'll leave from 50 on up higher. And so we enter that in this way. We start with the 1 minus, and then we go to distribution, and we up arrow to binomial CDF, which is B. We could have done alpha B if we'd remembered that. The number of trials is 100, sample size. The probability of the success each time, or we're going to assume that this is accurate, the 45% is accurate. So if that's accurate, we put that there. The x value we want is up to 49 actually. And then hit paste. If you have an older operating system, it'll go straight to here and do 1 minus binomial CDF, open parentheses. You just have to know the same numbers and you just have to know the right order. It's population size n, capital N is 100, comma, the probability of success, which is a proportion of successes in the total population, 0.45, comma, the x value, not a p hat value, but an x value of 49, which corresponds to 1 less than 50%. and that's what we're subtracting from 1 there. So this should give us the correct probability, about 18.3%. So there it is with the TI-84 screen. Now, on the TI-Nspire, the Nspire works slightly differently, almost the same. You just do binomial CDF. You get that by doing menu, and then actually you can find it under either probability or statistics, and then go to distributions and find the binomial CDF. Again, you give it the 100, the 45, but what's different here is, or 0.45, what's different here is you give it the lower and upper. So we want to keep the probabilities for 50 up to 100 for X, and so we put 50 and 100 there, and it returns the same value. So either way, about 18.3%. All right, one more application. Suppose that 67% of all dentists actually prefer toothpaste brand A. What is the probability that a survey of 50 dentists will report less than 40% preferring toothpaste brand A? Work this out. Press pause now. Well, once again, the population size is unknown, so even though the situation is probably technically hypergeometric, we will use a binomial distribution that approximates the solution. Now, this is going to be okay because the population of all dentists is a pretty large number, and the percentage of the population surveyed is pretty small. We're only surveying 50 dentists. So a binomial will work very well in this case. So if X is the number of dentists in the survey who prefer toothpaste brand A, then X has, or at least is approximated well by binomial distribution when N equals 50 and P equals 0.67. So what do we get here? Well, the probability of the sample containing less than 40% preferring toothpaste brand A is the probability that P hat is less than 0.4. Notice it did say strictly less than. So then we knew the probability that X is less than 0.4 times the sample size of 50. 40% of 50 is 20. So we're finding the probability that P hat is less than 0.4 is the same as the probability of the corresponding X being less than 20. Well, less than 20 means less than or equal to 19 in this case because there's nothing between 19 and 20 that has a non-zero probability in this particular type of distribution. So this is exactly the kind of thing that the probability works out on a TI-84. Let's go ahead and work that one out here. So it's just binomial. So second VAERS is distribution, up arrow, a binomial CDF, and the number of trials this time was 50. That's our sample size. The probability of the success is 0.67. In the population, the X value we're interested on is up to 19. Since this is a CDF, it does everything from the left up to 19. Hit paste and enter, and there it is. Now notice the E -5, that really means times 10 to the -5, means we move the decimal 5 places to the left, so that's going to give us 4 zeros, then the 2, 4, etc. So that's about that should be 4 zeros, and then the 2 are about 0.002%. Very small, almost zero there. Similarly, on the Nspire, you can use a binomial CDF, but the binomial CDF on the Nspire, you still enter the 50, you still enter the 0.67. I think it even comes up with a window as well, similar to this, where you enter the trials and the probability of success and the X value. But instead of the X value, you enter 2 X values, a lower and upper, in this case 0 to 19, and all the ones in between are included for the X's. So, and then you find their corresponding probabilities and add them up, which is what this does. And we get the same number there that we got on the TI-84. Okay, so that you should be ready to work several problems dealing with distributions of proportions now.